Let me hit record. Okay, welcome everybody. So this is the September technical presentation presented by IEEE MTTS Santa Clara Valley Chapter, or IEEE MTT-SCV. My name is Utkarsh Krishna. I'm the Vice Chair of this chapter. And today we are honored, and it's a great privilege for us to be able to present this talk, the title of which is Building 5G and SATCOM Phased Arrays and UaV Detection Radars Using Low-Cost Silicon Technologies. Our speaker needs no introduction. The distinguished professor and member of the National Academy at the University of California, San Diego, Dr. Gabriel Rebeiz. Welcome, Professor, and thank you once again for agreeing to do this talk. Before we go on to the talk itself, a few housekeeping slides, a few things to note. This meeting is being recorded, and it's being broadcast live both on Zoom and on the MTTAS Facebook page using Facebook Live. Links to the video and slides will be made available to all registrants. Please keep your cameras off and microphones muted to help with any bandwidth issues or background noise. Please post your questions in the Zoom chat window, address it to everyone, and we'll take periodic breaks, maybe every 15-20 minutes to answer them. Also, please ensure that your display name in Zoom matches the one you used to register. This will make it easier for us to check you in. If you did not register and were forwarded a link to this meeting, please send Utkarsh Krishna a private chat message, that's myself, in Zoom with your name and email address so that I can register and check you in. Also, please support us by becoming a member. Join IEEE at this link, or if you're already an IEEE member, please consider joining IEEE MTTS, that's the Microwave Theory and Technique Society. And we are active on LinkedIn. So if you're on LinkedIn, please follow the hashtag MTT-SCV to be informed about all future events. So the agenda for the talk today is here, and it'll be presented by our fearless leader and chairman, Mr. Jay Vanwit. Jay.
Thank you, Utkarsh. So the agenda for today is, as Utkarsh mentioned, he's just been through the COVID-19 updates. I'll go through the offices for the two chapters, for the two societies that are co-sponsoring this event. And then our treasurer will go through the speaker's bio and introduce Professor Rebeiz. Let's move on to the agenda. Okay, this is the updates and response to the COVID-19 pandemic. So as I believe everyone's aware, all the in-person meetings related to our chapter have been canceled, and that's why we have a virtual online webinar format only until further notice, until we get out of this pandemic. With regard to the MTT Santa Clara Valley chapter offices, I'm the chair, Jay Vanwit. The vice chair is Utkarsh Krishna. Secretary is Stan Tui, and the treasurer is Tom McKay. As I mentioned, this is a co-sponsored event with the Circuit and System Society, and the chair there is Imran Bashir, vice chair is Amit Jha, and the secretary is John Chen. I'll ask our treasurer, Tom McKay, to do the introduction of Professor Rebeiz. Tom.
Thank you, Jay, and welcome everyone. So I'd like to introduce Professor Gabriel Rebeiz, who is a member of the National Academy for his work on phased arrays and is a distinguished professor and the Wireless Communications Industry Endowed Chair at the University of California, San Diego. Professor Rebeiz is an IEEE Fellow, is the recipient of the Daniel E. Noble Medal, the IEEE Microwave Prize for 3 times, which I believe was unprecedented, and is the IEEE MTT Distinguished Educator, received the Educator Award, the IEEE Antennas and Propagation John D. Krause Antenna Award, and the IEEE Antennas and Propagation Society Wheeler Paper Prize. His group has led the development of complex RFICs for phased array applications from X-band to W-band, culminating recently in wafer scale integration with high efficiency on-chip antennas. Professor Rebeiz is considered to be the father of affordable phased arrays, and his 2x2 and 4x4 RF beamforming architectures, single and multi-beam, are now used by Renesas, ADI, NXP, P-Semi, Paragon Semi, Murata, Infineon, Cybers, Amplorion, Nokia, Qualcomm, Intel, Samsung, Boeing, Raytheon, and others, and most companies developing communication and radar systems. SATCOM affordable phased array development is based on his work and architectures. His group has published more than 850 IEEE papers, and he has graduated 102 PhD students and postdoctoral fellows. So, as has been mentioned, the title of Professor Rebeiz's talk is Building 5G and SATCOM Phased Arrays and UaV Detection Radars Using Low-Cost Silicon Technologies. Professor Rebeiz?
Thank you. If you can give me the, I am the host now. Okay, so how do I share screen? Okay, and I am sharing screen. And does everybody see my screen?
Yes.
In a large format.
In a large format, yes.
Okay. Well, thank you for inviting me to give this talk. And I know Utkarsh from National Instrument for a long time, and Tom McKay, of course, from Global. It is a pleasure to give you a talk and more on a little bit of the history and how we went on doing it, and of course, always with the latest and best results that we can share with you. We will be mentioning many names and many companies, and I hope that I will have the time to acknowledge everybody's work. It all started in 2001, which very soon is going to be 20 years ago, when I was meeting with Boeing and met with a person who is now a very dear friend. His name is Julio Navarro at Boeing. And we were working for Carson White, who is the VP of Boeing of phased array antennas. And he told us, I was a professor, I was visiting and spending a few days there. And he told us that we need to figure out how to lower the cost of phased arrays. And Julio Navarro and I, on his desk, at Boeing in Kent, Washington, in fall of 2001, we drew this. And this was effectively two antennas here, VNH with LNAs. And then we drew the silicon chip, and we told Boeing that you need to make a silicon chip that has all the phase shifters and VGAs and controllers. And we need to even make two simultaneous beams out of it. And you know what? It's gonna cost $7 per element when we do that. Now it is much cheaper than that. And Boeing loved this idea, and they immediately went and started doing silicon. And that was in 2001. Boeing funded us, DARPA funded us, everything at the University of Michigan and then San Diego, because I was there and then moved. And by 2007, after several chips, we basically made this 8-channel chip. That was 14 years ago. The first really highly complex RF beamforming chip, which worked from 6 to 18 gigahertz. And you have 1, 2, 3, 4 for 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8 channels, phase shifters, amplitude, and phase control, all on a single silicon chip. And this one worked from 6 to 18 gigahertz. And this was done by Kwon Jin Ko, who is now at Lockheed Martin Moorestown. I mean, there have been many, many chips, as you will see, but we culminated in the group a few years ago by a chip which is the first, one of the first 5G silicon chips at 28 gigahertz, which is a transmit-receive chip with 12 dBm transmit, 4.5 dB noise figure receive, phenomenal performance, became the workhorse of our group. And this was done by two students, Karim Kibaraglu and Mustafa Saginer. And look what we can do in silicon. We 12 dBm output, P1 dB after the switch, 20 dB gain on transmit, 20 dB gain on receive, 4.6 dB noise figure, including the switch. And that was done maybe 6 years ago, 5 years ago now, 6-bit phase, and all done, you know, as I said, by 2 students. For the entire chip, bumped, flipped, and we will see it doing in phase arrays. I mean, this is important because it shows how powerful is silicon. And in this case, this is Jazz, but we have, of course, other chips with Global and with Jazz. We only use Global and Jazz. But both of them, from 8XP to SBC H5 to 45 SOI, which is like a phenomenal process, it's unbelievable, unbelievable what you can do in silicon today in RF, not in digital. We all know in digital, but in RF. And this was also drawn by us, I mean, similar one and sketched, where we basically said, oh, look at the SiGe and then the gallium arsenide, and we can do LNAs, and we can do 2x2 and grow it in an area. I mean, this is 18 years ago that we drew these things, 2002 or something like this, that we drew these things. And we had this vision that we are going to make it between Julio Navarro and myself, who, as I said, you know, ended up being a phenomenal friend. We've taken this chip that Kwon Jinko has done, and we put it with bond wires. That was by 2007, 2008. And that was, at least from our group, the first time that we had a true phased array, a linear phased array, and that was 14 years ago with, you know, working at SATCOM at 11.7 gigahertz. And you could see scanning the beam plus or minus 60 degrees. So this is basically the idea, the fundamental idea is that you put 2x2 chips and you grow your PCB as much as you want, and then you add them together all the way to up-down converter, to an up-down converter. You can use full 8-channel receive for VNH. You can use full 8-channel transmit. You can use radars, transmit receive, or TDD SAT, you know, 5G COM. And for us, we insist on putting the LNAs outside of the chip, and I will explain to you why. Some people put the LNA inside the chip, which I believe is technically a mistake, and I will prove to you why. Now, one of the reasons you would ask, like, why have we have all the area? Why you know, is Samsung and Qualcomm and ADI and NXP and Renaissance and everybody is, you know, so so successful? It's not only the chip. It's also because the PCBs are phenomenal today. I mean, we can build PCBs with 160,000 vias and with 99% yield. The packaging is phenomenal. You know, today when you buy a chip, the packaging is like whatever packaging they're going to give you, it will work to 60 gigahertz. Could be it BGA, QFN, wafer level, CSP, whatever. It's going to work to 60, 70 gigahertz. Again, CMOS and SiGe improved tremendously, and also numerical and EM techniques to analyze. By 2010, we were working with Lee Paulson at Rockwell Collins, and we were building, I mean, we were actually sending chip IP from UCSD to Rockwell Collins. They were building them and packaging them and putting them on PCBs. And, you know, 12 years ago, 2009, 2010, we were building 20 gigahertz phase arrays for SATCOM receive as demonstration vehicles like this 64-element phased array. Now, at least I'm now going to start with SATCOM. And in SATCOM, we have always taken the path of having an LNA, which is placed at the antenna. And then we have an optional filter, which I will show you why is it so important. And then the 8-channel beamformer, which goes into VH, 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 VH. And these beamformers are phenomenal today. As you will see, they consume very, very low power, very low noise figure with the LNA. They have 128 state memory positions. They can, there is even bias where you bias IRF and you bias the LNAs so that you bias them versus temperature, and they work phenomenal. And by putting the LNA at the antenna directly, you have very little loss. You don't have this transmission line loss, which is maybe 0.3 dB. But for SATCOM, a 0.3 dB loss is a 0.6 dB lower of G over T. So it's very important to have the lowest loss possible. Now, let's talk about these LNAs. The recent LNAs that silicon has been able to produce is nothing but phenomenal. Nothing but phenomenal. I mean, you know, I did not believe that this is going to happen, but it happened. I borrowed this from Renaissance. Look at KU band, noise figure below 1.5 dB. And even below, they won't tell me exactly how much, but it's below 1.5 dB. At KU band, middle of KU band, noise figure is below 1.6, 1.7 dB. And at KA band at 20 gigahertz, noise figure below 1.9 dB. These are measured values. 20 dB gain and 2 channels, V and H, and every channel consumes less than 15 milliwatts. I mean, we are approaching to within 0.1, 0.2 dB of gallium arsenide pHEMT here. That is how good are these LNAs. Also, when you separate the LNA from the beamformer chip, when you separate them, the LNA, you can change the LNA every year. So every time you say, I'm in SIGI process, well, 45 SOI is very good, I jump to 45 SOI. As long as the bump is the same, you are very easy to change and get a better and better LNA every year, while you don't need to change the whole chip. So your customers, without doing anything, they just keep on changing LNAs from build to build and getting better and better noise figure. There is another big reason, and for it is for the filter, but I will explain this later. On the transmit, again, these transmit chips are dual polarized, and this is for SATCOM. We have to because they are circularly polarized, and you can be clockwise or counterclockwise. It could be elliptical, blah, blah, all of this. So you have to do circular polarization. And again, the chips are phenomenal. They are very high efficiency, as you will see, and 128 memory and power detector on every channel and temperature and blah, blah, and all of this, all packaged and you put on the PCB. So one question that I always get asked is, why a 2x2 and not a 4x4? It is a valid question. And why is the 2x2 better? Well, you know, let us look at this here. You could say in SATCOM, okay, I can put an LNA here and I would put an LNA here, so I don't care about the line loss. That's right. But on the transmit, here the line loss is maybe 0.2, 0.3 dB, while on the 2x2, where here the line loss might be 0.6, 0.7, 0.8 dB. So you lose half a dB, and half a dB is half a dB. In 5G, basically, yeah, let me see here, pointer options, and, oh, I don't want that. Pointer options, arrow, visible, okay. So in 5G, we don't use an LNA, but still the line loss here is much less than the line loss here. But I think there are more important reasons. This leads to a perfectly symmetric distribution. And here, it does not lead to a perfectly symmetric one if you want the shortest lines. This leads to the power being distributed uniformly over the array on the left, while on the right, you have 16 channels or 32 channels for dual pole 5G, and the power is very concentrated in a single chip. And also this one, if a beamformer dies, then you only lost 4 antennas. Here, if a beamformer dies, you lost a cluster of 16 antennas. So, which can really affect your performance. So at the end, I would say all of SATCOM have actually moved to a 2x2 beamformer. In 5G, we will see different. It might be this way, and we will discuss this in 5G. So I would say that by 2011, or even 2010, we were building at UCSD phenomenal chips, way before anybody was doing in 5G. As I told you, Kwon Jin Ko built this one, which is 6 to 18 gigahertz. Jung Gung Kim, transmit receive, 5-bit transmit receive, 2008, 2009 at 35 gigahertz. Tiku Yu, a 4-channel symmetrical chip at 24 gigahertz, 2007. Fatih Golkuk, a single human being, designed a 4x4, 1 transmit to receive phased array with 48 channels at 94 gigahertz as a single human being, one student, and that was done in 2010, 2011. Dong-Woo Kang and Chol Yong Kim designed a 16-element phased array at 44 gigahertz. And that is again done in 2008, 2009. And Sang-Young Kim and Osgur Inak designed the first automotive radar phased array again in 2010, 2011, with built-in test, full built-in test, and with up-down conversion mixers. And that was done later on with Bon Hyun Kyu for transmit receive, and that's how we build phased array automotive radars. I mean, I want to tell you that this is like 12 to 15 years before 5G, and we were doing all of this stuff. And at the end, I think Don Hyup did this with Osgur Inak 2 for a X-band phased array with built-in test. And this one won the IEEE Microwave Prize for built-in test. Now we were not alone. Raytheon, to give them credit, were also thinking the same way, maybe at the same level of integration. And by 2006, 2007, they were already building weather radars and low power radars using single channel chips and using SIGI. And that was IBM Global Foundry SIGI. I cannot tell you which SIGI it was. I'm not allowed to, but definitely it is Global Foundry SIGI. So companies were thinking the same way. I can tell you way before 5G, way before SATCOM, you know, what the commercial ones, Boeing and Rockwell Collins and so on have adopted it way before. This is work done at Rockwell Collins with Lee Paulson. And this SIGI chip, which is a 4-channel transmit receive, was designed by Rockwell Collins themselves in 2011, 2012. And they built radars with 768 elements without a single failure, and gallium arsenide TR modules here, because they wanted much higher than 100 milliwatts in their transmit power. And this is the pattern of 3 arrays that were built, each one 768 elements at 9.5 gigahertz, and the patterns of all 3 arrays on top of each other without calibration, to tell you the symmetry of the design. Boeing, by 2004 or so, has moved from their SATCOM from something that is nearly 18, 20 centimeter high to all silicon phased arrays. That was 7 years ago, 8 years ago. And that was the Panasonic announcement, and where the arrays are only 5 centimeters high. And in Europe, it was adopted by many companies, started the defense companies, Thales and Leonardo and Finmeccanica and so on, and they build these power radars where same thing with silicon and gallium arsenide. This is the Rockwell Collins array, which was published in the Phase Array Symposium by Lee Paulson. And you can see the silicon chip, you can see the gallium arsenide TR chips, and this is the pattern turned on with no calibration at all. Just turn it on and measure. We also built, under the Navy funding, multiple beam phase arrays. So if you have an antenna V and antenna H, you can break it into 4 separate channels and then do different amplitude and phase for every channel, and you do it over the whole array. And this leads to multiple beams coming from the same array. So one beam could be circularly polarized, pointed at this angle, the other beam could be pointed at another angle, and so on and so forth. Of course, you would need multiple beamformers, that means Wilkinson networks, to add all the chips together, but that's okay. This is the genesis of what we have today in 5G. This chip, which was designed by Dong-Woo Kang, and I think it was Dong-Woo and Chol Yong at UCSD, and Jung-gun, at all 3 Koreans from KAIST, who were in my lab. This was done in 2009, and it was the first time where we showed 4 simultaneous beams working at KU band from a silicon chip. The Navy loved it so much, they created a $320 million program to build phase arrays for them based on this chip. I cannot tell you what happened with this program. So today, when you go to Renaissance, you buy these chips with 2 beams. This is the 6112 at KU band, and you come in, you have an LNA, you have an external LNA, as we say, and then it breaks into 2 separate beams, and then you have basically 2 beams. And this is the transmit, and the transmit is generally 1 beam, but the receive is typically 2 beams. I mean, you can make it transmit with 2 beams too. The power is phenomenal. Today, 100 milliwatts for 10 dBm. And on the receive, including the external LNA, it's about 34 to 37 milliwatts per channel. Unbelievable. You can build a 1,000 element phased array with having dual polarization and consume 75 watts, which is a light bulb. Now, and this is how you would build it, where you would have the 2 channel LNAs that feed into the dual polarization chip, and then it comes in and you will have beam 1 and beam 2. This is a amazing bestseller at Renaissance. And all of the arrays built today have 2 beams. And it fits very, very nice at KU band. At KA band, let me say that there you can put a filter here, as you will see. There is ample space to put a filter, and this filter is to filter out the transmit panel, the transmit interferer. At KA band, Renaissance has the same thing. This is a transmit, and these are the receive, but they build a whole module. And the module contains the LNA and contains a bandpass filter and then the 2 beams, so that the user would just put the module and that's it. And the module has less than 2 dB noise figure and includes everything. And it even includes a phenomenal filter bit to filter out all the transmit. And the module fits perfectly on grid with a VH, and you come out and you have 2 beams out. Again, a phenomenal bestseller with less than 2 dB noise figure. So one of the main questions is that why do I insist on a filter? The reason why I insist on a filter is because it's an FTD system. Let's look at the transmit, which is 14 to 14.5, and let's look at the receive, which is 10.7. There is very little separation between them. So your LNA and your beamformer typically have still quite a bit of gain at 14 gigahertz. So you have an LNA with a gain of 20 dB and an input P1 dB of minus 20 dBm, normal LNA. You have a beamformer with an input P1 dB of about minus 30. So the input P1 dB of this whole channel is minus 50 dBm. That's completely okay with SATCOM because you're receiving a minus 180 dBm signal. That's completely okay. But it's not okay if I have an interferer. So I have a huge interferer because I have a transmit array, even though it's at 14 gigahertz, but it's radiating a phenomenal power, 80 dBm, 90 dBm, 48 to 54 dB watts. And other than having this coupling, 30, 40 dB coupling down, when it scans, I have reflections from the radon. Unless I put them so far away from each other and use 2 separate radomes, which increases the cost, I will have reflections from the radon. So this large signal is going to overwhelm the receive channels. So what do? You put a filter. And this filter is after the LNA and it kills the transmit. So we did this. This is the LNA. And after the LNA, there is an embedded filter in the PCB. This is the work of Gokhan. These chips are from Renaissance, and this is the work of Gokhan Goltepe. And you see these 2 filters. And this is also the same LNA and the same beamformer, but there is no filter to see the difference between them. And look at the difference. Within in-band, it's the same gain. But then out of band, when we put the filter, you have 25 dB rejection of the leakage transmit signal before it hits here into the beamformer. And look at the noise figure. The noise figure of the entire system from here to here is 1.5 dB. And 1.53 to 1.59 with including of the filter. That's without the filter, with the filter. And the recent ones are even better. These are LNAs generation 1. LNAs generation 2 are 0.2, 0.3 better in noise figure. And that's what it is that, you know, every 6 months, Renaissance gives us new LNAs with better noise figure, basically. And you could see that the noise figure is not affected. But most important in the input P1 dB. This is the input P1 dB in your receive channel. But once we hit 14 gigahertz, the input P1 dB becomes that of the LNA, and it's minus 20 to minus 17 dBm. So I can handle all the transmit leakage, and it is not going to affect my performance. The last thing I want to talk about is voltages. One should not think of the system by itself, of the chip by itself. One should think of the entire system. A typical array that's 1,000 elements running at P1 dB at maximum power is going to consume 100 milliwatts per channel, 2 of them VNH, 1024, that's 200 watts. If I have a 2.4 volt chip, that's 83 amp. But if I say, no, I want to go to very low power CMOS, that's 1.2 volt chips, that's 166 amps. I need twice the copper. I need to spec my PCB to be twice as heavy copper in order to handle twice the amps, just the resistance and amps, so as not to have the voltage drop. Furthermore, most of my power modules are coming from 28 volts. If I go to Renaissance and I say, hey, I want a 28 volts to 2.4 volt DC to DC converter, that's an 88% efficiency. If I say I want a 28 volt to 1.2 volts carrying 166 amps, you are lucky if you get 82%. You get like 80% efficiency. And this power is taken off the top. So it is much, much more efficient to work with a higher voltage system when you are dealing with a large power on the transmit and working with 2.4 volts. And 5G understands this. And 5G, all the PAs are running at 2.5 to 3 volts because they could not run anymore at lower voltage because of the current. SATCOM did not understand it. That's why SATCOM, you have chips at 1.2 volts, chips at 2.4. But this is a clear indication that SATCOM systems are much more efficient if they run at higher voltage, like 5G. So, I mean, look what we have built. These are real systems. This is a Rockwell Collins, 2400 element, 2 beams on receive, 15 dB over Kelvin. Look, this is me. This is not a wax museum. This is actually Gabriel Rebeiz standing next to this that was built by Lee Paulson at Rockwell Collins Cedar Rapids. And 1400 elements, 48 dB watt transmit. And these things are a reality. I mean, they are a reality 5-6 years ago. You know, way before 5G or everything, they are a reality. And and when you turn it on, no calibration whatsoever. The whole 2400 element array, you turn it on, you measure this pattern. That's phenomenal. That's phenomenal. And it's all based on the 2x2. And of course, when you calibrate, you can get anything that you want. So in our lab, this is the work of Abdul Rahman Al-Juhani, where he's using the first generation IDT Renaissance chips and building a receive chip very much based on the 2x2 and dual polarized, a receive phase array. And these are the measured patterns at 11.7 gigahertz scanning to 70 degrees. I dare to say this is without calibration. No. This is phase calibration, but no amplitude calibration. And look at it, what we can do. And this is in the E plane, and this is in the H plane. The best is that we build several PCBs, and if we take the phase calibration of PCB1 and we apply it to PCB2, we see nearly exactly the same patterns. Look at that, even the cross-pole, even the frequency response. I mean, it also tells you that that the chips are so close to each other that you are kind of calibrating transmission lines rather than you are calibrating chips. This is phenomenal. I mean, this means that I can move calibration from board to board to board and not calibrate every board. And also, you can make any pattern you want. You can make a flood type pattern. Let's say you are on a UaV looking down. You can make a cosecant square pattern. That is a pattern of a UaV talking over a long distance. You can make a, monopulse pattern and so on. And these chips, which were the Renaissance chips, version 1, were built by two students, Tumay Kanar and Samit Zahir. The entire chips, transmit, receive, KU, KA. I sometimes say, it's unbelievable what I ask my students to do, but you know what? They always deliver. I ask the impossible from them. They come in, it's like to graduate, you have to do the impossible. And you know what? They do the impossible and they deliver and they graduate. So Abdurrahman al-Juhani showed with his work in the phase arrays that really you don't need lenses anymore. You don't need transformational optics. If you have a phase array that is low cost in transmit and receive, you can synthesize any pattern every few microseconds to do anything you want. Now we move to the next generation of phase arrays, and this one is built on the Renaissance F6101 chip. I'm sorry, this is a mistake. It should be F6501 because that's a transmit, KU band transmit chip. And it's a 1,000 element array built by Gokhan. And we've just presented it at IMS 2020, so I'm not going to talk a lot about it. You can find it in IMS 2020, but look at this. Look at simulation of amplitude and phase, of the pattern after calibration of amplitude and phase. Look at that. This is measured versus simulated. And here it is scanning plus or minus 70 degrees with cosine to the 1.1 and generating 43 dB watts per polarization under uniform illumination. Kevin Lowe built a 256 element phased array at Ka band, 29 gigahertz. And you could see the chips here. And you could see a driver chip in the middle to drive it. This was also presented at IMS 2020 by Kevin Lowe. And we have 63 dBm, 33 dB watts AIRP. And you could see the patterns as cosine to the 1.1 theta. This is at 29 gigahertz. And these are the patterns for a 1,024 element phased array at 29 gigahertz at turn on. I mean, I want you to pay attention to something. This thing on the right, on top, is no calibration whatsoever. A 1,024 elements times 2,048 elements, because this is CP. And you measure the pattern and you find this. And when you calibrate it, of course it is better, no complaints, but that tells you how good are these chips. And this is done with the Renaissance F6502 chips. So, and this is it versus scan angle all the way to 70 degrees under uniform illumination. And it has a EIRP of 45 to 46 dB watts under circular polarization with an axial ratio of better than 0.5 dB, a cross-pole level better than 30 dB. Now, one of the most amazing thing about phase arrays, and I am sorry if you are a gallium nitride person because we are beating you. We are beating you so bad here. Look at the ACPR versus scan angle for 100 megahertz, 200, 500, 8 PSK, to QPSK, but look at it versus power. You can operate at P1 dB. You can operate at PSAT. P1 dB plus 2 to 3 dB and the EIRP and the ACPR is minus 30 dB, minus 30 dBc. No gallium arsenide, gallium nitride can do that. And we have written papers, and we're trying to understand it, that it's the contributions of all the IM3 contributions of all these 1024 amplifiers that are not adding perfectly in phase, and therefore you are not having a degradation as you go to P1 dB and so on. And this is with alpha of 0.7 and a PAPR of 4.4 dB. So even if you are at P1 dB, you are shooting to 4 dB above. And at P1 dB plus 3 dB, you are shooting to 7 dB above. And look at the ACPR over all scan angles. This is phenomenal, absolutely phenomenal. And that means different than a gallium arsenide or a gallium nitride SSPA, which I have to operate at 2-3 dB back off. Here we operate at P1 dB plus 2 dB. And we still meet the linearity of SATCOM because the arrays are so large. So at UCSD now, we have a 4,000 element array with 64 by 64 elements and 56 dB watts at 10 dB amp per antenna with 6 dB taper, because these arrays are built to this. I mean, this thing is equivalent to a 50, 60 watt gallium nitride SSPA, and is built by chips that cost $1 to $2 a channel. This is where we are now. Now, let's look at the power consumption. The Renaissance chips are 100 milliwatts at 10 dBm. And if you drop them, you know, to 6 dB taper and so on, they are like 75 or 80 milliwatts or below, while still, you know, giving you the 25 dB gain and so on. So if we are, and their noise figure is 1.5 dB or better at KU band and 1.9 dB or better at KA band, which means that a 1,000 element array at KU band is 10.5 dB over Kelvin. And a 1,024 element array at you know, KA band is 9.5 dB over Kelvin, because there is a 0.5 dB approximately noise figure difference, which transfers to 1 dB in G over T. The receive is dual beam. There are filters on the receive. It consumes less than 80 watts on the receive, and it consumes less than 180 watts on the transmit for 44 dB watts. Now, 44 dB watts is assuming a 6 dB cosine taper for reduced side lobes. And so you're getting EIRP loss from it, about 2.5 dB EIRP loss. And you are doing 10 dBm per channel at the center. I mean, today you can build a phenomenal system for 250 watts. 400 or 500 watts before, you know, these arrays would consume 1 kilowatts and 2 kilowatts. And with these new chips, you know, we can build the whole thing for very, very reasonable. I mean, for 5G people, just to tell you, this is 74 dBm, okay? I mean, that is a huge phase array. I mean, a huge power, a huge ERP. And you know what? SATCOM wants 48 dB watts and 50 dB watts and 52 dB watts for the GEO. And for the LEOs, you know, one can make much less power per element and then meet their requirements with a 1,000 element array. So I can say it has been a phenomenal success with SATCOM. And these new chips are phenomenal. The radar chips, and perhaps let me go back here to give, you know, credit. Oh, well, so, no, sorry. This is SATCOM. Oh, So these radar chips, well, the one that you see today were built by Rockwell Collins, and many companies, you know, Raytheon, Boeing, blah, blah, all have built their own chips. A very good commercial chips that you can buy, which covers X and KU band, is the ADI ADAR 1000. I'm sure you've seen it at IMS 2019 and 2020, and I see it now in many, many systems. I cannot mention the companies, but it's been used in many, many systems, and I would say it has been a very, very successful chip, and it, you know, clearly, how you say, has a genesis of coming from a certain group in the world, basically. So now let's go to 5G. So historically, clearly SATCOM and radars have taken this technology before 5G. And look at this. This is the Boeing 4,000 element receiver. They announced it at Satellite last year, 2019. This is a public picture, and they announced the Ka band SATCOM, and this is the transmit, and this is the receive. I mean, one can clearly figure out that they are both around 4,000 elements, and the receive is actually 2 beams, and following very much like the Renaissance chips. And so Boeing is a phenomenal company building SATCOM phase arrays using all silicon technologies. So let's go to 5G. Well, I always say that today in 4G, when we communicate from the base station to a mobile unit, and it is low gain antenna to a low gain antenna to a low gain antenna. And if we look at Marconi in 1900, it was his Nobel Prize poised picture, we find that this is the base station, here it is. This is the mobile unit, here it is. It was a low gain to low gain. 120 years, and we have not changed the way we communicate. Now, clearly, we know that if we have a high gain antenna at the base station and a high gain antenna at the receive, then we can have a much, much better link. So rather than this being 6 dB for the base station or 8 dB and this being 0 dB, if this one is now 30 dB and this one is now 15 dB, you have 40 dB additional link margin, 50 dB additional link margin. So it is a phenomenal advantage. But you need to build phase arrays. Because once you make a high gain beam, it becomes very focused. So you have to steer the beam. And that's what all 5G is about. It's about basically directive communications, steering the beam, fixed wireless access or 5G base stations and so on. It's about having a directive beam to you, either sub 6 gigahertz or millimeter wave, and tracing you, tracking you, and basically having a high link margin, gain transmit time, gain receive. Obviously for you too, you will have a 4 or 8 element array, which is not a lot of gain, but enough to close the link. So it is about more bandwidths. Now we're going 100 and 200 and 400 and 800 megahertz bandwidths. It's about coding, a lot of coding. That means phenomenal modems, phenomenal channel modeling, phenomenal channel equalization. Noise figure, I think we are all around 4 or 5 dB, theoretical limits. PA, power and efficiency, we're still working on it. And then high gain antennas and spatial diversity. And you know what? This is exactly what SATCOM is. This is the Hughes EchoStar, maybe 17 or 19, I don't remember, and how they sectioned the US for 100 beams at Ka band. That's exactly what SATCOM is about, except that the SATCOM base station is at 36,000 kilometers, and which is a GEO. Now, of course, we have the LEOs, and they are much lower, and the 5G is at 360 meters. But that's it. It's the same idea. So I borrow this from Qualcomm. 5G is the era of directional comps. It's all sub 6, millimeter wave, all of this stuff. And the FCCs all over the world have listened, and they've opened all of these frequencies. So let me take you on on a journey of how we build these things, and how there is now much more variety compared to SATCOM, because really SATCOM is 2x2. There is no one in the world building SATCOM except 2x2. Here, you basically are building smaller phase arrays, which could be 16 by 16 or 4 by 4, and then putting an up-down converter. And some of these arrays are double polarized, as we will see. Now, so the main question comes, how do I do that? One way is I will continue with the 2x2, add them, and then I will put a filter and I put an up-down converter. The other way is I am going to put everything on a single chip. The whole thing, the mixer, the LO, the whole thing, all on a single chip, and then feed the arrays. At the end, both of them work, and both of them are good. The companies that are delivering chips to Ericsson and ZTE and Nokia, who want 22 dBm per channel for high linearity and high power, have all adopted this approach, which I call, the UCSD approach. We came up with it, and it is, and these would be Renaissance, and they would be NXP, and they would be ADI, and Infineon, and many others. The companies that are developing smaller powers for the cell phones or for low power, 35, 30, 36, 40 dBm EIRP low power units are mostly adopting this for low cost. But remember, these chips cost a lot to make. So because you're making the synthesizers and multiple channels and this and that, so you better be selling a lot of them. And anytime you want to change something, you have to have a huge team that is changing a very complex chip. Here, you basically can say, I can make the beamformers in SIGI or 45 SOI, but I can make the up-down converter in 28 nanometer CMOS. I can make the LO in 16 nanometer, whatever. I can mix and match technologies. And typically, people have mix and match technologies because these here are generally very high power in the base stations. While in the cell phones and the UEs, they are not 20 and 21 dBm, or let's say 18 to 20 dBm. They are more 14, 15, 16 dBm. And the 3 or 4 dB difference is quite large. Also, the heat distribution here is uniform, while here the heat distribution is all centered on a single chip. And then if you go, let's say you want to do multiple MIMO, you can either do it this way, or basically you'll have one chip every 16 elements. And I'm not saying A is better than B. Both of them are good. And you see companies are using A and B depending on the power level. This is the way I say it. We are all good engineers, and we will all make the right decisions based on the system requirements. So some have made the right decisions to choose a 2x2 and its derivatives, 2x4 for dual pole. And some have made the decision to use a 16 or 32 element for more complexity and more channels on a chip, depending on your application. The other thing is to discuss is that, how do you scale when you are building a large base stations? One way is I will do it all RF up to, a certain level. And the other, as we discussed, is I will have a mixer and so on, and the LO multiplier, and then I will add. So as we discussed, it depends. Generally, I would say that some people are even putting the LO here if it is a fully contained unit, like in a mobile phone or in a small CPE, or a small, UE or something like that. But again, both of them are possible. I think what is more important is how do you put it on the PCB? So, and really there's a big difference. And I will show you there is A and B, because everybody is either going this or that. So one is that I take the chip, and I don't care what the chip could be. The chip could be either all RF or line, or could be RF and a mixer. But I take the chip and I put the chip directly on the PCB, and then the PCB contains the antennas. All the SATCOM work you've seen is like this. A lot of the 5G work is like this, with and without a mixer on the chip. Samsung presented something at ISCC with a mixer on chip. ADI chips don't have mixers on chip. Renaissance chips do not have mixer on chip. But the main point is that the antenna is on the motherboard PCB. The good thing about this is that you have direct access to the chip and you can directly cool it. Another one is what we call interposer or antennas in package. You have seen Qualcomm doing it like that, Samsung doing it like this, and many other companies, IBM, for example. In this case, you create a self-contained unit, and typically the RF chip here definitely includes the mixer, because the only IOs coming out are IF, LO divide by 4, and of course SPI and control and so on. And this is what some people refer to it as interposers, and some people refer to it as antenna in package. And you could see companies either going this way or going that way. There is an issue here you need to think about, and it is that you do not have direct access to the chip to take the heat out. So the way people have taken the heat out is that they make a hole in the motherboard PCB, and then they can put a thermal glue and touch the chip and take the heat out from the back. In this case here, you have a direct access to the chip and you can take the heat out. So I'm not saying A is better than B, but we have two high volume solutions happening today. Some people would say, yeah, but this PCB is going to be an expensive PCB now because it has to carry the antennas and the beamformer and whatever, but mostly the antennas, while this PCB is really a low-cost PCB because it's only carrying LO and IF and baseband and, and clock and SPI. However, this module is expensive too. Definitely, when you see the publications, all cell phones are going like this. And for UEs, CPEs, it's left is both, but all base stations, big base stations, are going like that. So pick and choose. Both of them work well. Just pay attention to the heat if you choose to go antennas in package. So,
oh, Professor?
Yes.
I'm not sure if you'd be interested in taking a few questions right now. There's quite a few that have come in through the chat window.
Absolutely. Let's do it. Well, you know what? Let me finish just a little bit and then I'll take questions. Just give me 5 more minutes because I know where is a good break.
Okay.
Okay.
Sounds
so
good.
This is one of the first 5G phase arrays that was ever published, done by, as I said, the chip was done by Kerim Kibaroglu and Mustafa Saygener. And it's unbelievable. And not only did they build the chip, they built the whole phase array, they built the whole PCB, everything. This is the work of 2 people. It's, I mean, again, impossible, but it worked. It was phenomenal. It was published in RFIC and MTT and JSCC and whatever you want, and TMTT, and it worked without any calibration. You can even see how symmetrical everything is. And you turn it on without any calibration, you get these patterns. And then without any calibration, you get basically 50 dB dynamic range and 2% EVM and 64 QAM, and it was phenomenal performance. That's the chip that was at the beginning of the talk where I showed you the 5G chip. And we've taken it with an 8x8 and did gigabit per second at 5 kilometers. That was maybe 4 years ago. The same people, Kerim and Mustafa, mostly Mustafa, designed the first dual pole, dual beam chip. And now you can buy this chip from Renaissance, from ADI, from Infineon, they presented it, and others. And it's virtually the same identical architecture, which is VNH, and you can have dual beam at the same time. And then you go into a beamformer. And this phase array here was designed by Ahmed Nafi. And and he did such a phenomenal job that you look at the V and H response of the two beamformers and of the chips over frequency, plus patterns of V and H, cross poles of below 30 dB between them, extraordinarily low EVM, because otherwise it will be limited by the cross pole. Then, and phenomenal performance. Well, both of them are working. All done by one student. The whole thing is Ahmed Nafi. Not 2 or 3 or 5 or 10 people, only one human being. That's it. Renaissance has now phenomenal chips, either single pole, 5280 with 13 dBm, or the new dual pole, dual beam with 18 dBm and 11 dBm linear at less than 3%, running 400 megahertz 5G NR. And again, following the same architecture that was published by UCSD, I would say ADI has shown similar chips, and Infineon too. Maybe I have access to Renaissance more than the others, but this is a extremely competitive performance. And maybe I can, before we show a lot of work, maybe I can stop now and take questions.
Okay, so I'll just I'm trying to group as it makes sense, but one question is, what's the typical cost of these SIGI beamformer ICs, say an 8-channel, a 4-channel dual polarization?
Well, I can tell you, I am not privy to tell costs because these are under NDAs, but I will tell you one thing. The cost drops phenomenally quickly versus number of chips purchased. If you purchase 100 chips, the cost is going to be quite high. If you purchase 100,000 chips, the cost is going to be extraordinarily low, shockingly low. So the answer is it depends on the number of chips that you purchase.
Okay, thank you. So I think on slide 21, there was a question about the location of the filter, and I think the questioner was curious about where that filter went.
Well, I think filterment. If you get the module here, the filter is already in the module. It's between the LNA and the beamform. It's already in the module, and you don't need to worry about the filter. If you at KU band, the filter is embedded in the PCB, in the PCB layers. We basically, you can see it here. The PCB is in the layers underneath M1. There is a filter here.
Great. One of the attendees is observing that most of the ICs seem to have around 10 dBm output power, and this was a while back, I think, about 10 minutes ago, about 10 dBm output power and 3% EVM. And is there some kind of silicon? The question is there some kind of theoretical limit for silicon and 3% EVM and that sort of thing?
Not at all. Actually, the 5G chips are 18 dBm output P1 dB. In SATCOM, most of SATCOM runs at 8 to 10 dBm because there is what we call a mask. You cannot radiate a lot of EIRP unless you meet a certain mask. And the mask is narrower and narrower beam widths as you are increasing your EIRP. And therefore, it does not pay to have a very high power per element. And generally, most SATCOM is running at 8 to 10 dBm per element to meet the SATCOM geo mask. At LEOs, actually, it's much lower. You're running at maybe 4 dBm per element and not 10 dBm, and your array is smaller. So that's why. Now, the 3% this 3% is running QPSK at P1 dB. The 5G, which is 3%, 11 dBm, is running a peak to average ratio of 11.7 dB, 400 megahertz, 64 QAM, OFDM, 100 kilohertz spacing with much, much tougher waveform. So really, you cannot, I mean, they ended up both being 11 dBm, but the 5G is really running at 18 dBm and it's 7, 8 dB back off, while the SATCOM is running at P1 dB or P1 dB plus 2 dB. I mean,
right.
Yeah. So,
right.
so don't mix them together, basically.
So maybe this ties in a little bit to the EIRP comment. There was a question about what if you had an element failure on say, a 256 element array?
Effect.
You know, what would happen?
Nothing.
Like if
nothing.
Typically, if one of
the answer is generally a very easy way to think about it is that your side lobe level is equal n failure over n array squared. So if you have an element failure every 200 elements, you will get 1 over 200 square side lobe, a side lobe showing up at 1 over 100 is 40 dB, 1 over at minus 46 dB. Now, obviously, your side lobes typically out of your radiation and taper are minus 22, minus 23, so you will never see it. But it will generate a side lobe, which is typically element failure over total number of elements. So let's say I have a 1,000 element phase array and I have 10 element failures. I will see a side lobe of minus 40 dB, which will be 10 over 1,000, which will be 1 over 100, which will be minus 40 squared, minus 40 dB. So really, we know in phase arrays that you can generally lose 3 or 4% of your elements, and it will be okay.
Got it. So there was a couple questions around 1024 arrays. One of the attendees was asking about how the work that you're sharing would be in context with, or how you would include a 1024 University of Waterloo result. And then another question, sort of maybe in the same vein roughly, is can you scale up from 1024 to 2048 elements?
Well, I think this is the 2000. This is 4,000 element. So you can scale up to anything you want. So this is 4,000 element array, 4,096. Well, I mean, the University of Waterloo has not published their result, and have not, you know, published their power and so on and so forth. If there is a publication, please send it to me, and then we can look at it and reference it in papers, because we're going to present this paper and we'll put it in a table to compare it.
Got it. Okay. There's some interesting questions around non-idealities with that I think are interesting. One is when you do the antenna in package approach and then mount it to another lower cost board, I'm not really familiar with this term. I'll be frank, but the question is the performance for scan blindness better for that in that scenario, since the dielectric is not continuous and any surface wave that you might, parasitic surface wave you might get in the other implementation is broken up.
No, total bullshit. Sorry. Okay. The scan blindness will happen even if you have 16 element array. I mean, once the flow mode happens, it happens. So if you design it bad, I mean, obviously, if you have a antenna and package with 2 antenna elements, then yeah. But if you have an antenna and package with 16 antenna elements, you will see the scan blindness, period. It doesn't matter. You will see it.
Okay. So another sort of second order implementation or system metric question has to do with blocking from other users, and the questioner is sort of asking, would some of these NPath techniques that have been put forward for filter, that can filter, these mixer first type ideas, I guess, do you think that would be an interesting idea? Well, oh, I'm sorry.
Yeah.
If you're not speaking, could you mute? So the question is
in my opinion, we do not see it, because the NPath filters or the mixer first has a pretty high noise figure at 30 gigahertz. We have not yet seen the clocks required in order to do that. And these phase arrays are running at 4 or 5 dB noise figure, including the switch, which means the LNA and the switch is about a dB loss. That means this LNA or the whole channel is about 3 dB noise figure, 3 to 4 dB noise figure. So therefore, the mixer first is not possible. The other thing about the mixer first is that, you need such wide bandwidth. You need 400 megahertz, 800 megahertz, and now 1.2 gigahertz. How are you going to follow the mixer first with op amps, and which has such a wide bandwidth in order to give you the zero, from the op amp response, so that to reflect back at the antenna? So I don't think we will see mixer first anytime soon.
Mr. Amit Sahu, can you mute your phone, please? Thank you.
So in the antenna in package scenario, are the beamformer IC and the antenna elements fabricated together? I'm not really sure.
No. The beamformer IC is typically just a silicon IC. I mean, IBM has showed it, Qualcomm, and all of this. We see it at the end, and it is done in advanced CMOS processes, and then it is bumped on a laminate interposer, and then the antennas are on top. So just normal packaging, basically.
Got it. So one question, and maybe this is sort of helpful on a tutorial level, is you commented that there a 0.3 dB loss in front of the LNA would translate into a 0.6 dB G over T degradation. Could you clarify that?
Well, because in SATCOM, your T antenna is 20 Kelvin. It is, so it's not terrestrial. Terrestrial loss equal to loss, loss equal to noise figure, because you are looking at a T antenna that is 290 Kelvin. You're looking at the ground, you're looking at the room,
right,
like that. But in SATCOM, you're looking at a cold sky, which is 20 Kelvin to 30 Kelvin. So any loss increases your antenna temperature. TA is not 290K, it's 20K. So any loss greatly increases your noise temperature, which effectively worsens your G over T, because you have, greatly increase your T.
Very good. Let's see. Just trying to scan. There was a question about our folks putting these arrays onto curved surfaces. Is there any, I suppose there's a finite curvature, these are flat chips at a certain scale, but I guess the question is, is it possible to put these on a curved surface, and maybe, would that be an interesting?
Well, cell phone people are trying to put them on curved surfaces at the edges. It all depends on the size of the chip and the material and the bumps and so on. I would say this is more mechanical engineering and chemistry rather than electrical engineering. For us, curved or no curved, we know how to work with it, but how to manufacture it, how to make it curved without the chip breaking or any of the stuff is very challenging. To my knowledge now, there are no millimeter waves, except for, crazy defense stuff, but there is no commercial millimeter wave on curved surfaces.
So there's a question here that I'm sort of hesitant to put forward because I know there's some, although I'm not close to the debates myself, you can get into a religious debate sometimes on these architectural choices. But then I have another question after this. So, but there was a question that for 5G, the attendee was commenting that the understanding was that hybrid beamforming was the architecture of choice. Could you comment to that?
Well, yeah, this is hybrid beamforming. Hybrid beamforming is when you take analog phase shifting up to a certain point and then you use a down converter. That's a hybrid beamforming here too. You have analog phase shifting and then you go, after you sum them up, you go to a down converter. Now it could be VNH, but they are still hybrid. I mean, there is no other solution at millimeter waves because we have not yet figured out how to make digital beamforming at 28 gigahertz. In sub 6 gigahertz, we have done that, and all arrays are digital beamformed. But at millimeter waves, because of the number of elements and because of the bandwidth, and now they're talking about carrier aggregation, where they can be separated by a gigahertz apart, where you can have 200 megahertz here and 200 megahertz somewhere else. We have not yet figured out how to make these ADCs and DACs and these large number of elements and handle all the data and make digital beamforming at the element. So it is very, very hard. So today, I would say, out of the hundreds of thousands of base stations shipped by Samsung and Ericsson and Nokia and everything, everybody is following something like this, which is
great
beamforming.
Got it. So I had a question, which is this work, pioneering for high-end applications. You talked about scale and the low cost of these technologies. I'm wondering what trends you see for millimeter wave sensing, let's say, right? Because it is a sensing modality that is becoming low cost and can be incorporated with others, for a range of things.
Let's talk about this at the end, because we have few slides on this at the end.
Very good. Okay, I think that pretty much covers it. If I missed anyone, they could resend their question, but I think that covers it. Thank you very much, Professor.
I think somebody sent a question to me privately by mistake, so I just want to relay that question to the professor. So the question is, how do you feed the RF signal to the chips? How do you implement the Wilkinson resistor?
For us, and we have the Wilkinson resistor is implemented as a lumped element that we place on top. You can go buy them from DigiKey as just regular resistors. And you know what? We measured them and they work all the way well to 40 gigahertz. So we don't use embedded resistors in the PCB and all of this stuff. Just regular Wilkinsons on top and lumped elements, and that's it. Lumped 0201 resistors.
Okay.
Okay. So again, here, I'm not saying A is better than B, but I would say that when I look at big base station stuff, more and more people are going this way, where you buy the chips and they are high power chips, and then you can directly attach them to the back. And when you look at lower cost stuff, such as inside mobiles, inside computers, inside this and that, and very high volume, more and more are going this way. But also these are lower power chips too, lower power for, PA, and lower linearity and so on and so forth. So both of them are good, both of them are useful, and both of them are built in the millions of units per year, left, A or B. So going back to, we talked about this. And we talked about the dual pole, dual beam. Yeah, I mean, you could see here, look at these resistors here. These, and this is all published in MTT. These are the Wilkinson resistors. So, yep, they work very well. Look at this, you know, look at VNH. And then we basically, I think we stopped around here where we say that the new generation of 5288 from Renaissance, they have 18 dBm output P1 dB, and we measured them in my lab, and 11 dBm linear at less than 3% dBm, which is, you know, phenomenal, running 400 megahertz, 64 QAM, 5G NR, and you know, and people can just go buy this stuff. So we've taken the 5280, which is the single pole transmit receive, and we built a 256 element phase array, which is the picture that was placed on the web. Utkar did this, and this is it, the scanning plus or minus 60 degrees with 6 dB cosine taper with absolutely no calibration. You turn it on, you put your network analyzer here, you go to the far field and you measure. No calibration whatsoever. And this is what you measure. These chips are phenomenal as in repeatability. And this is a 4x8x8 for 4x4 MIMO. And again, these are the EIRPs for 4 quads. Again, no, at PSAT in this case, or P1 dB, I don't remember, with no calibration whatsoever. If we calibrate and we apply a 10 dB taper, look at this. We can get 20 dB side lobes down, and look at theory and experiment. This work was done by, I think, Yu Chen and Chen Ma and HC, and but I think it is mostly done by Yu Chen, yes. And this work is done by Zhe Zhang in my group. With the calibration and the, you know, and the side lobe levels. You run in this case 256 QAM, and you know, look at this at 256 QAM, 100 megabaud. I mean, we could basically get you know, we could get 57 dBm, 58 dBm out of that, literally out of these arrays. Very phenomenal performance. We also built a new one based on the F5288, and this was published at IMS this year. And it includes the LO. We used the commercial LO. We did not build our own synthesizer, and a two-channel transmit, two-channel up and down converter to IF. The Renaissance, it's, I think 5728 is the up and down converter. You know, phenomenal harmonics, extremely low harmonics, and you turn it on and these things work. Look at the single sideband rejection. You know, at 4 gigahertz IF, you are at 120 dB single sideband rejection. Why? Because I can put a filter embedded in the PCB. Even at 3 gigahertz IF, I have like 75, 80 dB single sideband rejection. And these were what I call generation 0 chips. They gave us kind of like, oh, you know, take these chips for free. And they delivered the 5 dBm linear. But now the new generation, as I said, you know, the one that is being sold is 11 dBm linear. And so with the 5 dBm linear, we were able to get 45 dBm, but that includes the entire system. That includes the up-down converter, the LO, the receive, the chips, the whole thing. But the new ones, which, you know, we are measuring now with 11 dBm EIRP, we push this to 51 dBm at less than 4% entire system EVM. But also look at the harmonics that are generated. And this is harmonics at RF minus 10 dB, backed off by 10 dB. And effectively, you don't see the LO, you don't see the image, and all other harmonics are, you know, 50, 60 dB down. And that's also because of the filter here. The people who put a mixer on the chip cannot get such harmonics because there is no way to put a filter. There is no way to put a filter. When I go back here, and that's the reason why they are lower power, and is that once you put a mixer here, then you have two choices, and Qualcomm has published it, and Samsung has published it. The only way to do it, on the transmit, if you want to put a filter, you have to choose a very high IF. Then you choose an IF of 9 gigahertz or 11 gigahertz. Then at that point, you can put a filter. But you cannot choose an IF of 3 gigahertz because there is no filter on an IC that can filter at this level. So you can check the ISCC publication of Qualcomm and of Samsung. They are very high IF. And then after they sum at 9 gigahertz or 10 gigahertz, then they put another down converter that goes from 9 gigahertz, to baseband, and then they feed into the model. But putting a filter outside here, you can operate an IF of 2 gigahertz and just go directly into a RF SoC or into a modem, and you're done. Again, I'm not saying one is better than the other, but I'm saying that this is how they are designed now. And this is 39 gigahertz. We do the same thing at 39 gigahertz, no problem. You just build it this way. It works well. And we don't have time, but we've done it at 60 gigahertz. And I would say Intel has published some very good work done at 60 gigahertz. This is the work of Yu Chen. And again, look at this. We can go up to minus 25 dBc, we can have 44 dBm. And you could see calibration barely improves it, barely improves it because they are so well calibrated naturally because of the design. And versus scan angle, it doesn't matter. Now, we are very proud that, and we say it was just pride that, a lot of companies have embraced this technology. And, you can go to Mobile World Congress and you can see all the wonderful things from Ericsson and Nokia and Samsung and Qualcomm and you name it. And then, we should be proud of this. And you go to Samsung booth and then you see the 39 gigahertz and the 28 gigahertz and all of this stuff. And again, we are proud of this. So, excellent and good. Now, in handheld, clearly, without any doubt, Qualcomm totally and completely dominates, which is good. They are in San Diego, so it's always very good. And they have definitely adopted this approach for the hand mobile and computers and low power units. Of course, I cannot show you their chip, but I can show you what has been published in ISCC a few years ago, which you would consider generation 0 or generation 1. And again, they are following the module approach, and they have synthesizers and LOs and 2 beams and 2 this and 2 that. And ISCC and also Samsung has published similar chips and have built base stations like this at 28 and at 39 with CPEs and base stations. And I would say Qualcomm is definitely following this approach. I don't remember if Samsung was antenna in package or their chip was directly on the main PCB. I am sorry, I cannot confirm if it was A or B, but it was very impressive work, and you could see it in the presentation of this year in February 2020. And these are the modules that are being developed, and this is of course from the web. And what can I say? As Carl Sagan used to say, billions and billions. Now we will say millions and millions, and pretty soon, hopefully, we will say billions and billions for modules inside cell phones and inside computers and handhelds and this and that and all of this stuff. Now, there have been enough teardowns to say that these are 4 antennas and each one is dual polarized, so the chip should have 8 channels. And if you go to iFixit or any of these, you can see some of the teardowns of these modules. Now, finally, and we have been funded to do this work, there is no reason that these arrays should stop at 5G. They could become radars, they could do traffic monitoring, they could do many, many functions. And Aaron Wang and Tom Phelps in my group have proved it at 60 gigahertz and now at 28 gigahertz, where rather than take two arrays and do a MIMO, we take one array and we turn it into a transmitter, and one array we turn it into a receiver, which is, yes, just use the transmit channel alone and the receive channel alone, and run an FMCW waveform, which is a very simple automotive radar waveform. And you've taken tiny UAVs, tiny UAVs like DJI Mavic, which is a phenomenal UAV. And we measured its RCS, and it is only 0.01 meters squared. It has an RCS as small as a bird, especially if you are coming at this angle to it, because it reflects down, and look at the RCS there. And you can calculate, a transmit and a receive, and your EIRP and your noise figure and so on and so forth. And you say, pooh, I can measure something at 2 kilometers. And sure enough, this is the transmit array, and this is the receive array, and this is the UAV flying and flying and flying, and we still have 10, 11 dB SNR with, I think, only 50 milliseconds integration time, which means that you can do, 20 look directions or 20, searches per second. Yeah, I mean, it's phenomenal. These things work so well. And so to answer you, Tom, these things can be used as multiple sensors, and they can have, if you could turn all your base stations to be either comm or radars or sensors all at the same time. Just maybe 95% of the time they are comm, and 5% of the time they are monitoring the airspace or the ground or something like that. You can count the humans. We counted students passing by. I mean, we can detect Boeing 737s flying from San Diego Airport. I mean, we can do anything we want with something like that. I mean, look at this.
Very interesting.
This is
so may I ask a question about is that a commercial funding that you're getting that from, or is it government? Or because to me that's very fascinating. The observation that these things could be dual purpose out there in the world, and it's very fascinating. I'm just curious if it's public or it could be shared. Where the interest is coming from. Is it primarily a civilian, or it's corporate, commercial, or is it?
It is U.S. government, I would say.
Got it. Okay, very interesting.
So, I mean, and here we come to the conclusion, and that's it. The end of the Marconi era is here. I mean, we have entered into the Directive Comp era. Obviously, you know that Huawei and so on have built 300,000 base stations below sub-6 gigahertz for China, and they have embraced sub-6 gigahertz 5G. The world is slowly embracing it. Millimeter wave is coming. I mean, it is there. I mean, if you read the reports, there are hundreds plus thousand base stations have been built between fixed wireless access and base stations, and they are continuing to being built. And many companies, are doing excellent work into this. I mean, can we build phase arrays? Now we can build phase arrays at any frequency. 24, 31, 37, 42, there are 47, 54. If you look at our publications, which I have not put here, with Bhaskar Rupakula and Samit Zahir and so on, and Umut Kodak, we have wafer scale phase arrays running 256 element dual pole, dual beam at 62 gigahertz, doing 10 gigabits per second. Or phase arrays where there are still chips on PCBs all the way up to 66 gigahertz, doing 30 gigabit per second at 64 gigahertz. I mean, we can build phase arrays all the way to 94 gigahertz with no issue whatsoever. I mean, IBM, I mean, Global Foundry, 22FDX and 45SOI are phenomenal technologies, up to 100 gigahertz and beyond, and 440. And let's not forget 8XP and 9HP, and let's not forget Jazz, SVC, S5, which is turning out to be also a phenomenal technology. I mean, you know, you have so many at your tips, and you have the packaging, and you have the built-in test, and you have the wonderful material, and I would want to finish with something, because that's very, very important. And I mean, look at this here. I mean, look at this here. Where it is. Look at this here. We send this to Kyocera in town, and we send them this board, and we send them a board which is a 1,000 element phase array with the drivers, with the SPI, with everything, and they give it to us in a week, and there is not a single failure on a single channel. I mean, that's how good packaging is and assembly is. We send them 20 of these, they come back, not a single failure anywhere. We actually go search for failures, and we can't find a single failure. I mean, Kyocera is so freaking amazing.
Whoa. I'm sorry, can you mute that for a second?
Yeah, Kyocera is so amazing. I mean, there is no failures, period. We have never seen a failure. I mean, obviously it comes also that Renaissance chips are at 0.5 millimeter pitch, and they are BGAs, and so on and so forth. But I mean, this thing, 1,000 element phase arrays come back, 0 failures, period. Now, not one, not two, a lot of arrays come back, 0 failures on any channel. This is how good assembly is today. If you work with a good assembly house, now I'm sure each one of us here, 100 of us have had disaster stories with assembly people, but if you work with a great assembly house, I mean, it's amazing what they can deliver to you.
So Professor, there was a couple more questions.
Don't let me just finish. So,
okay.
And I'll take all the questions. So effectively, that's it. You know, we have the silicon, we have the PCBs, we have the assembly, we have excellent engineers working on system level and on antenna design. We have the modems. We have everything that we want to build anything that we want up to 100 gigahertz. I'm serious. That's it. We have made phase arrays affordable, and all of us together in the microwave communities, we have changed the world. And that's it. Thank you.
Thank you, Professor. So if I might just ask a few additional questions that came in, and a few of these are sort of like related to those kinds of issues that you run into. I mean, you emphasize that you turn these arrays on and they work without calibration. Of course, you have done calibrations. And I think you're sort of emphasizing that the repeatability of the silicon technology and that's in some of the chips. But
and the repeatability, there are several. Repeatability of the silicon technology, the repeatability of making these PCBs in terms of vias and epsilon R, the quality of the board, and the assembly. All of this put together is resulting into phenomenal phase arrays.
So what happens over environmentals? One of the questions is, you know, there's talk about, you mentioned low Earth orbital satellites, for example, and you know, maybe what happens over temperature? Is there special calibration that needs to be taken into account for power over temperature or array balance over temperature?
No, the answer is no. And the reason is all of these chips come with PTAT and with corrections, internal corrections versus temperature. You really don't need to do anything. The phase shifter steps are the same versus temperature. The VGA steps are the same versus temperature. The output power might drop a little bit like any silicon process if you heat them up to 85 or 95, but they are very well designed and they go, you know, all the way to 95 and even 105 degrees. But in terms of the phase beam, the beam quality, in terms of the beam, yeah, the phase step, I mean, nothing changes versus temperature. Things are very, very stable. And generally a phase array, because of this uniform heat source coming rises up all together and cools down all together. You don't really have hot spots, I mean, for a well-designed phase array. So yeah, no.
What about G over T over temperature?
G over T over temperature, well, any loss that you have will add to T antenna. As we know in an attenuator, it will be loss times T physical. So if your array heats up, then your antenna loss and any transmission line loss would contribute more because it will not be loss times T naught, it would be loss times T ambient, you know, which would be, you know, so if that's why you should have to keep the loss as low as possible so that you do not contribute any of the stuff to your T antenna.
I think I understand. Thank you. Let's see. Oh, there was an interesting question with regard to isolation. For example, when you know the transmitter is outputting, and what about the isolation between the transmitter output and say its input? Right? Are there couplings that occur that you know that are showstoppers? And then another kind of practical question, which I think it's great we have our attendees kind of asking these sort of valuable experience questions. You commented about the 0201 resistor, and it works to very high frequencies, but you know maybe you need to choose the ones that are close to 50 ohms or something. Is there anything with that? So I guess there's sort of two implementation questions. It's sort of isolation, and then the other one is related to that Wilkinson comment, which is amazing low cost 0201 resistors, but do you have to select for them or somehow know their value?
Well, I mean, Wilkinson needs 100 ohms, and a Wilkinson resistor is 100 ohm, not a 50 ohm, and we have measured them before, and instead of 100 ohms, there might be 70 ohms minus, you know, J something. So that's okay. The Wilkinson still works well. We can put a little bit of inductive portion to tune out the J, and it works very well. One can just go to HFSS and take any 0201 and see its dimension and model it and put it there and get its capacitance and compensate for the capacitance a little bit. So these things work well. As for the input-output here, I don't understand if you're saying if the coupling between the transmit to the input here in the chip, because I mean, I can comment on the Renaissance chips that the transmit feeding back to here is below 55 dB. I mean, it's very, very low that it does not distort anything. So
I think that's good.
Yeah.
Yeah, I think that was the question, yeah. Okay, well, I think generally there's a few other bits and bots but I think that pretty much covers the questions.
So
I guess, actually there is one more that I can't help but asking, because I remember attending a long time ago the discussion between you know, high power tubes and Butler matrices, you know, versus these IC approaches back in the very old days of gallium arsenide ICs, and the question is maybe what are the benefits of this technology or the trade-offs of this technology relative to maybe other techniques that might be out there. I mean, is there?
Tom, there is no other thing. That's it. We've killed everything. There is, once you think about how to make a low-cost phase arrays at dollars per channel, or $1 or $2 or sub $1, whatever, depending on your volume, in 5G and whatever and so on. Once you figure out how to make a phased array, you will not do anything else. It's like, you're driving a Rolls Royce, and I made your Rolls Royce to be the same price of a Toyota. Why would you ever want to go and, drive another car? I mean, that's it. I mean, what you need are three things. You need good chips, you need a good fab house for the board, and you need a good assembly house. That's it. I mean, obviously you need good design and good system people and, all the right engineering, but from a manufacturing perspective, just find yourself a good chip manufacturer, find yourself a good house to make your PCBs, and find yourself a respectable and honest assembly house, because these guys, a lot of them are not respectable and not honest, believe me. I mean, I'm sorry if there is any assembly people attending. That's why you gotta find yourself some real professionals that know how to assemble in high yield. And that's it, you're done. I mean, look at this PCB, and look at the PCB of your Dell computer that is inside your Dell computer, and open it and see that, Dell has figured out how to make 100 million PCBs and 100 million laptops in a very repeatable fashion. And look at this PCB here. Every time we send it to Kyocera, it comes perfect, period. It comes perfect. Every time we ask chips to come back, they come perfect. Our PCB manufacturer, it comes perfect. Just align yourself, your supply chain, and phase arrays will be very doable. Just, and then your rest is just design, HFSS and this,
right,
and just design your system.
Well, I think that's a great closing comment to this here. I do think there's a few questions, but I think in the interest of time, I think we'll end the Q&A question session and here. And I just want to thank you, Professor, for spending nearly 2 hours with us here today. All of us at the Microwave Theory and Techniques Santa Clara, San Francisco Society chapter really do appreciate you taking the time to share with us the learning over decades, and it's really thrilling to see this and to get a new level of appreciation for it. I certainly have myself. So thank you.
That's absolutely true. I just wanted to say, so we had, between Facebook Live and Zoom, we had close to 170 people watching. So this is probably, not probably, without doubt, our best, most attended talk so far. So thank you very much, Professor. This was really a very informative session.
Welcome, welcome. And if anybody has any questions, they are welcome to email me. I mean, the email is on the first page, so you can email me.
Thank you, Professor Rebeiz. Thank you.
Thank you.
So with that, we'll close our proceedings. If you have any questions, as the professor said, you're free to email those to him. This session was recorded, so we will make the links to the video and the slides available to all registrants. So in a day or so, you should receive an email with those links. So thank you everybody for attending. I hope you all found it as informative and exciting as we did. So with that, we'll close our session. Thank you once again, Professor, and we'll see you all next time. Goodbye.
Thank you. Talk to you soon. Bye-bye.